Okay, we're gonna get rolling today. Just in terms of announcements, like Meet the Professors is this Friday. Um, so stop by then if you want. I believe it's from 12 to 2:30 in like 3,000 or 11. Let's see. I got the email. Oh, it got moved. It's now 3-3 in Kemper 1131. So stop by there if you want to just talk with us or hang out with other students and get to know us a little bit better. I unfortunately won't be able to be there because I'll be at office hours. But you can talk with the rest of us, get to know us a little bit better. There'll be pizza there, so free food. So stop by if you're hungry or just want to get to know us better. Your midterm should be out today, so you can finally get started on that, even though it's way past the midterm of this course. Expect it to be very similar to quizzes 1 and 2, so nothing too different there. And then we should be able to get the rest of the questions out to you fairly regularly.
Mm-hmm. So we have 1 week for this homework. Are we going to have 1 week for the next homework as well?
So the next homework's already posted, I believe, right?
Yeah, but there are 2 more, right?
That was 1 and there was 2 more total, right? Which is.
Oh, this is the last. There's like no more.
No. There should be homework 4 should be up.
Oh.
I believe it should be. There's only 1 question for homework 4.
Oh, okay.
But
Oh, thank you.
Yeah. So they should all be up. I probably should give you guys a little bit more time for quiz 3. I thought we have like 3 weeks of lecture left, I guess it looks like, including this week. So I thought we only were down to 2, so I can give you guys a little bit more time on that assignment. Anything else before we get started today? What? Yes. Any other questions before we get going? Give you more time for homework 3. Okay, so we're going to pick up from where we left off. We're still talking about integrating our code into C. We're going to do one more example of a recursive function that utilizes Boolean. And then we will also talk a little bit more about stack frames and kind of give you some visual examples of like how they're created and when they're destroyed and how they can be, again, they're useful because they give you constant offsets to your local variables and to your arguments. Oops. Oops. So let's say we wanted to write a function that could find the sum of a list of numbers, but we want to do it recursively. Does that make sense? You guys have probably done this one before many times. So what should we do first in writing this function? Yeah, write the C code, right? It should always be the very first thing that we end up doing. So I'll just get rid of all this. Okay, so if you're going to find the sum of a list of numbers recursively, what's our base case? Right, because that's what you should always start with when you're working with recursive functions. What's the easiest list of numbers that I could give you to sum up? Easier than 1 number? No numbers, right? Generally with recursion, always when your base case is going to be you have nothing, because nothing's really easy to do. So what's the sum of 0 numbers? 0, right? So if len is equal to 0, we can just return 0. Otherwise, how can we define the sum of our numbers? Right? So we know that to reach our base case, right, we have to reach 0 numbers, right? So how could we make our problem a little bit smaller so that it's closer to having 0 numbers? Right? If I had this list of numbers, 10, 20, 10, or whatever, stop typing, 10, 43, 76, how could I make this list of numbers be a little bit closer to being the empty list? So yeah, you can decrease the length by 1. You can just say -1, but what does that mean? Right? Like, if you want to make this list of numbers smaller, what do you have to do besides just say length -1? Again, think about it naturally as a human being. You have this list of things. Do you want to make it smaller? How do you make it smaller? It's not necessarily some of them, but we could just take an element out. If I take one element out, wouldn't you agree that the list is smaller? Right? So again, in terms of just thinking as like human beings, like if I want to make that list number smaller, I just need to take one thing out of it, right? If I want fewer toys in the toy box, I take a toy out of it, right? So you might decide that we want to take, say, the 10 out, the first element. So I have the 10 and this list of numbers 43 and 76. Well, what would be fantastic to know about the rest of those numbers? Like, just the absolute best thing to know about them. The most useful thing for this problem. Those sum of the numbers, right? That would be fantastic, because if you knew what that sum of those numbers were, what could you do with the 10? Just add 10 to it, right? Does that make sense, right? You could, if you knew what the sum of the rest of the numbers were, right, you could just add 10 to it, and that would be the sum of all of the numbers, right? Well, what function happens to find the sum of a list of numbers? This function finds the sum of a list of numbers, right? And if you believe it works, you can just call it, right? So otherwise, right, if there's more than one number, you could just say, well, it's the first number, num's at 1, num's at 0, right? Plus, well, the recursive sum of the remainder of the numbers. Now, how do I say the remainder of the numbers? I know that length will be -1, but how do I say the rest of the numbers? All the numbers but the first one. Just nums plus 1. Right? Nums plus 1 is the pointer arithmetic. Right? So at the beginning, where's nums pointing to? Nums is pointing to the 10, right? The first number. So then if you say add 1 to this pointer, well, it's going to point to the next integer. And because arrays, they're all consecutive in memory. They're next to each other, right? The next number after 10 has to be the 43, right? If we start our list of 2 numbers from 43, we'll have 43 and 76. Does that make sense? Are there any questions about this example besides the fact that maybe you need to practice recursion? At least that mindset, because it's not something you do all the time, but it is a really, really useful skill. Okay, so what do we do down here now? Right, we got our C code. That was step numero uno. What do we do for the rest? How do we translate it? Well, we have a prologue, but the prologue needs to be at the beginning of the function, right? Do we even have something that marks the beginning of our function? No, so what do we need to mark the beginning of our function? A label, right? So our label should be rexsum, right? And where should this label be at? Should be in the text section, right? So don't forget .text. And, well, we want to use this symbol outside of this file, right? So how do I make it usable outside the file? .global rexsum, right? and then we'll have our .equ word size as 4. So yeah, the first thing to do is the prologue. Prologue. And what's the first thing that we do in the prologue? Push %EBP. Then move L %ESP to EBP. Then make space for the locals. Right now, we don't necessarily have any, right? But we could just, so right now, if we want to, sub L 0 times word size from %ESP, right? Make space for locals, which we don't have any right now, but if we do, and then we might have to save some registers too, right? So great. We've gotten that done. There's the prologue taken care of. It's the same thing each and every time except for the amount. The next thing that we might want to do is our EQUs. So where is nums going to be at? How far past EBP will it be? Right, so what's the stack look like at this moment, right? So here we have EBP. It's currently pointing to, right, the old EBP, right, because we just pushed it. Right, above that's going to be, at +1, will be the return address. And then above that's going to be the parameters. Which parameter first? Nums. And then we'll have len at +3 words, right? And again, if you don't want to think so hard every single time, after you do the prologue, the first argument will always be 2 words past EBP. And then you can just start counting from there. So we want to do our EQU for nums, and it's going to be 2 times the word size past %EBP, and then .EQU, we have len, which will be 3 times the word size past %EBP. There is probably some way of making the EQU just fully substitute to the entire expression, but I haven't been able to figure out how to. Okay, so we got that taken care of. Now we have to translate this line. How do we do this? And given that we have to refer to len multiple times, what's probably a good idea? Putting len into a register. What register would you like to put it into? Sure, EAX. So EAX will be len. So move L what into %EAX? Len past EBP, right? So now here, if we're doing this equality, right, we're going to do this if statement. How do we do it? Compare L 0 with EAX, and then what? Jump J and Z, jump if not 0, or you could do jump if not equal. Either one will work, right? Because what we are translating this into is len minus 0 equal to 0, and then again the negation is len minus 0 not equal to 0. So jump if not equal, or jump if not 0 to, right, the else, sure. Down here there's the else. And if we succeed, well, we need to do this. So how can we return 0? Move out $0 into %EAX, and then We can't just ret. What would happen if we just did ret right now? Where would we return to? Not the prologue, but the epilogue. Right? Because if we jump back to the prologue, we're going to go back up here and do it all again. Right? But if we did do ret right now, if we did have ret right here, where would we go back to? Yeah, we go to old EBP, wherever that happened to be pointing to, and we start executing instructions that happen to be on the stack, which is not where the instructions are actually stored at. So we'd probably get a segmentation fault if we did this a ret right now. Oops. So we're going to jump to the epilogue. Okay. Well, yeah, that's why we put 0 in there. No. What does it have? Oh, okay, I see what you're saying, because EAX has to be equal to 0 to enter the if statement. Is this line redundant? Yes, I guess you could say that, yes, this line would be redundant, and you could just jump straight to the epilogue if you wanted to optimize it, right? So you could optimize this line out if you wanted to.
Where do they go with, how come you don't have like count them if you push EDX and EDI and ESI,
Where do they get
sitting?
would be on the stack, right?
But how come then like the indexing for all the other stuff doesn't change?
Well, the indexing wouldn't change because we did blah 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 blah. Because we're using the base pointer to access the elements. If we had been using ESP to access them, then yes, our values would have to be updated because we now have more stuff on the stack. But because we're not using ESP, but we're using EBP, and EBP is not moving, we have a fixed offset every time, right? And if we were adding elements, right, the saved values, they would show up beneath the arguments, down here somewhere. So now, right, we just have one more line of code to translate. How do you want to do it? Well, if we get nums at 0, then what do we have to do? What would happen right after we did nums at 0? We'd have to call a function, right? Which would probably, if you put nums at 0 into EAX or ECX or EDX, it would just immediately overwrite it. So it might be useful to rearrange it so that instead of doing it in this order, we do it in this order, which is no different arithmetically speaking, but it allows us to do a slight optimization where we can do the function call first and then do it. Though given that we need to access nums, it's probably a good idea to put nums into a register if we really want to optimize, because it's used twice, not just once. But we also know that if we put into EAX or ECX or EDX, it'll be overwritten by the function call. So we'd have to choose to put it where? Well, we'd have to choose to put it like an ESI or EDI or EBX, right? So maybe we'll have EBX will be nums. EBX will be nums, right? So we can just say move out nums past %EBP to %EBX. But if we're using EBX, what do we have to do? Save it first, right? So depending on how we want to do this, we might say sub L 1 times word fries from ESP. So this will be at -1. We'll have old EBX, and then dot EQU old EBX will be at negative. Oops. I forgot commas in all of these, didn't I? Old EBX will be at -1 times word size from %EBP. Right? Or if you wanted to just be lazy, you could just push it, and it'll show up on the stack. And then, so first thing that we need to do is move out %EBX to old EBX past %EBP because the subtraction just made space for it. So save old EBX before overwriting it. Okay, so I got to do this line now. How can we do the call? We can't call rexsum because what's the problem of just saying call rexsum right now? Doesn't have any arguments, right? So it's going to have a bit of issue running correctly if we don't pass it its arguments as expecting. So how can we pass it its arguments? Well, if we're going to be putting the registers, if we're going to be putting these values onto the stack to call the function, what order do they get pushed in? Which one would you push first? Would not push nums plus 1 first. Remember, arguments are pushed right to left, reverse order of declaration. So we need to push len minus 1 and then push nums plus 1. So, yeah. Can you move len minus 1 into len past EBP? But like, so you're asking, can I write this using a loop? Of course you could write it using a loop, right? You've totally written the sum of a list of numbers using a loop before. But here we're doing it recursively, right? So yes, you can totally solve this problem iteratively, but we don't want to right now. So how can we get len minus 1 onto the stack, given that we already have len in EAX? Right, so you might say like decal %EAX, right? This is len minus 1. And then push %EAX. Okay. Then push %EBX. And then call rexsum. Well, do we need len anymore in our program? No, so we don't have to save it, right? So if you need it in the future, yeah, you have to save it. If you don't need it, just let it get trashed. Okay, so the call completes, right? So let's remove our arguments. So addo $, 2 times word size, 2% ESP, clear args. So now we have the return value. It's in EAX. So how do we add nums at 0 to it? Well, we need to get nums at 0 into a register. So how do we get nums at 0? Well, we don't necessarily have to get nums at 0 into a register. We just need to get nums at 0 and then add it to EAX. But remember, like, so what do we want to put here into EAX? What should be the statement on the left-hand side? What's going to be nums at 0? Well, I mean, EAX or EBX has become nums plus 1, right? This is EBX. Okay, so yeah, sure, you could do something like decal %EBX, and then, oops, cancel. And now that we've decremented it, what can we put over here? Okay, so great, now EAX is equal to this. And so what do we need to do now? Say it again? On the right of? You mean, so why isn't it like comma word size? Because that does word size times the scale, or the word size times the index, right? 4 times the index. What's our index if you don't give it? What's the default value of the index if you don't specify it? The default value of the scale, if not specified, is 1. The default value of the index, the second field, is 0. So 0 times 4 is 0. So wouldn't hurt, but it's also kind of like no point in doing it because you'll get the same answer. So what comes now? Well, yeah, but we just had the epilogue, right? Because the sequence comes right afterwards. Okay, so what do we do in the epilogue? Yeah, so move L percent, or move L, oh gosh, old EBP past percent EBX to EBX, right? Restore old EBX, and then no, I'm going to do popping, right? Remember, the next line is always going to be move L EBP to percent ESP, clear locals and temporaries, right? Because right now, at this point in time, ESP is right here because we did the subtraction. So if you make ESP be equal to EBP, ESP moves up to this line here, and old EBX is now gone, right? It got removed from the stack because it's at an address lower than ESP. And then, last instruction, return. Go back to where you called from. Are you guys happy with your solution? Do you have any questions or comments on it?
It is supposed to be, you said, callable from C?
Yeah.
I'm a little confused as to how that works.
So to make it callable from C, you just have to obey the GCC C calling conventions, right? Those 3 rules.
But like, how do you, let's say, you have, like, can you spell this out? So, okay, I guess my confusion lies in first of all, what C can call, like, do you call it from a different C file?
Yeah, we're going to call it from a different C file.
Okay, and how do you describe how it gets called?
Rec sum parameters.
So
You call it like any other C function. We're going to call it like you essentially did the compiler's job and translated this C code into assembly.
Okay, yeah,
right? So you have this function, and so if you want to call it, you just call it.
But like rec sum, so what's nums and len? Like, how do you make nums and len become a thing?
I'll show you in 1 second. Yeah.
Do you not have to pop percent EBP before you compare?
Oh, did I forget to do that? I did forget to do that. Thank you. Pop percent EBP. Any other comments or concerns you have about it? Yeah. What? Why did I pop EBP? Because I pushed it up here. Right? Because remember, the epilogue just undoes the prologue. So let's say we now want to jedit main.c. And we'll just do this like a rough and dirty one. So over here at the top, we'll make a declaration of recsum. So int recsum is going to take in integer pointer nums, and then an int len. And then here we have int main. So here is our nums. Maybe we just have 10, 20, 30, something like that, right? And then our length is going to be equal to 3. Sound good so far? And then we're going to need to pound include stdio.h. And then don't forget to return 0 here. And again, these names, they don't matter what the names are. They can be whatever we feel like. They don't have to be nums and len. They can be whatever we kind of choose to be for inside of main. And then we might say something like int total is equal to rec sum nums and len. So call it like a C function because it's callable from C. And then we might just say like printf the sum of the numbers is %d and then total. Yeah.
I don't really get though how nums and len, what registers do they go into?
They're not. They're going to be pushed onto the stack.
So,
Right?
So you pop off nums and then pop off len?
Who is we? Well, main or our function?
Your function.
Recursive sum?
Yeah.
No, it's not going to pop them off because it didn't put them on the stack.
They're on
Right?
the stack, right?
They are on the stack, right? So like when we do the call, right, len and nums are already there. Like when we're called, this is what the stack looks like. ESP is pointing here at this point in time, and then nums and len are right above it.
Okay.
Because
In that comment you say EAX will be len. Why will it be len?
Because I put len into it and use it like it was len. Again, that's just like internally inside of this function, I will be using EAX as len.
Yeah, but like I guess my confusion comes from len and nums are on the stack right now.
Sure.
At what point do you take them off the stack?
The function that calls me, so main will eventually remove them from the stack. Just like when we called ourselves, right? We called ourselves down here, right? And then we cleared off the arguments, right? To the function that we called. So any functions you call, you're responsible for getting that stuff off the stack before your function returns. Like essentially, like after you call a function, once it's done, the entire state of the computer needs to be identical to what it was before the call, except for EAX, ECX, and EDX, and the contents of memory. Those can change, right? But everything else must be exactly the same. So we make sure that happens. Yeah?
So the add L to $32 WS, that undoes the push EAX and the push EDX, like that pops it off?
Yes, that pops those values off. Because remember, we talked about how push is implemented. It just subtracts 4 for each push from ESP. So since we did it twice, add 8 to get that be restored back to what it was. Yeah.
I feel like this line after the deco EDX, like every time we call the function again, doesn't it overwrite where that old EDX, the original one was stored?
But each time it's going to be stored at a different spot on the stack. Right? Because every time the function gets called, right, it redoes this entire epilogue, right? Or the entire prologue, right? So it's going to make space for a new EBX, old EBX, right? And that new old EBX will save the current value of EBX, whatever it happens to be.
So like when does it actually like go back to like the way original one, like at the bottom?
So your question is, when does it return back to whatever the original one was? After the function was called? After the return?
Okay.
Right? Because
it's resetting itself every single time.
yeah, right? Because if you think about it, like if we have our C function, right? Let's say len, right? The original time we call len, we call it with 5. How many instances of the len variable will there actually be once we get to the case where len is 0? 6, because 5, 4, 3, 2, 1, 0. 6, right? So there'll be 6 instances of the len variable, 1 for each instance of the function that was called, right? So same for us, there are going to be 6 instances of old EBX, 1 for each version of the function that was called, right? But you're seeing the internal details of that actually going on. There's also going to be 6 copies of nums, right? Because we called it 6 times. So again, you can also see like this is going to be slower than just iterating through the list because you have to keep creating new variables, keep pushing arguments on the stack, keep doing the calls. That's why recursion tends to always be slower than iteration because you have all this extra overhead of calling the functions, pushing the arguments, creating copies of the variables, etc. Any other questions before we try running this sucker? Yeah.
Like for Mark 2, when you have a function that you call before the recursive call, does that function, are they arguments or locals?
Well, so the locals for one function might be the arguments for another function.
So you treat them as arguments with arguments, treat them as locals.
Yeah. Right? So right now you're seeing like behind the curtains, right? You're seeing all the implementation details of how everything is happening. But it's been no different than what's been going on before. Your locals are locals to that function, and your arguments are arguments to that function. We'll show you an example of what the stack frames look like in a moment, where function 1 calls function 2, calls function 3, with different arguments and different locals, so you can kind of like visualize what's going on. Okay, so let's try compiling this. So gcc-m32 -wall -w error -g, don't forget the -g so that you can compile, main.c recursive sum.s. Oops, undefined reference to old EBP. Old EBX. Try that again. One more time just to make sure. Oh gosh, stop hitting the button. Okay, great. It's done. Right, so let's try running it. So if everything works out, we'd expect to get the sum of 10 plus 20 plus 30, 60. So let's see if we get that. You guys made a mistake. What? Can you tell us? Well, maybe we can, I don't know. Apparently DDD hasn't worked out so hot so far. But let's see if DDD can like help give us some information about what's going on. So we call our function, right? So let's just run it and see what goes on. So it's segfaulted right here on this line, so we should probably look at whatever EBX happens to be. So P $EBX, EBX is 2,645. That's not good, right? So somehow EBX got screwed up. So if we come back to our code and we can try and look and see, well, how did EBX get screwed up? So EBX is supposed to be nums. So it looks like, yeah, we moved nums in there. It's 2 words past EBP. So what we might want to do when they're debugging is see kind of like where it screws up. So if we go back to what happened to DDD? Nope. There we go. So what might also be useful is seeing like what is len at this point in time. So if we wanted to see len, right, it's on the stack, and we know it's at position 3 on the stack. So the way that you do this is you lie to the compiler and you tell it that EBP is an integer pointer, and we want to look at word 3 past EBP. And it's at 1. So it screwed up on the call to 1, but it was fine prior to that, right? So that means something maybe happened in the recursion, and we kind of need to see like, well, did we call it with a wrong value, or did it get overwritten in the recursion and we forgot to like restore it correctly? Now, did I restore it correctly back here? So move old EBX back to EBX. It's at -1. We subtracted 1 times the word size. But again, probably best not to guess, but to debug. And I'll slide this over because apparently you guys can't see that. And we'll break at recursive sum. And then we'll try running it again. So we're calling it. We put at len in here. We get EBX. So here we're going to graph display $EBX. It has a number, some funny number, but if we kind of wanted to see it, it's being interpreted as an integer. So you probably want to see like what's its value as a pointer. So I will attempt to cast it into an integer pointer. That's a big number. That makes sense, right? Seems fine, right? And so here EBX is fine. We might also want to look at the contents of our stack. So we can graph display integer pointer $EBP add 0, and then if we want to look at our stack, well, we know that we have 2 arguments, but we also have old EBP and the return value. So we can say, well, maybe I want to display 4 things, right? Garbage, garbage, pointer, length, right? So this is old EBP, right, was placed on the stack. This is the return address, where to go back to, and then our a pointer to nums, and then our length 3. So let's say we continue and we do it again. We establish our guy. It's fine. Seems to be cool. He has 2 in there. And then if we keep going, right, like there seems to be a sensible value on the stack, like negative 12,447, again, that big number. And again, every time we like added 1 to it, it should go up by like 1. So we continue. It went up by 1, right? This is kind of where things we saw were going wrong. And decal, decal, inkle, inkle, push, call. Right, we're doing ourselves at 0 now. We go to the base case, hopefully. So we jump to the epilogue. We move old EBX back to EBX. But old EBX got 5, 6 on there. So notice that EBX ended up with some funny value in it. But EBX didn't start with a funny value over here. Right? If we kind of like scroll back up. Old EBX, again, 2 words past there, there's still this funny number. Right? But did we put old EBX? Or did we put EBX nums into EBX? We did. So maybe I want to set a breakpoint here. But I want to add a condition. Properties. And that condition should be when basically %EAX is, or $EAX is equal to 0. And then so we can restart, run it again, continue, 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 continue. It's fine. And so we're about to do this. So did EBX get a sensible value? It does. It has a very, very large value. Right? Move 0 into EAX, jump to epilogue. Now old EBX must have not had something sensible in it, because the prior call to EBX had a funny value there. Right? Because EBX got a sensible value from the stack, but the old EBX had a wrong value there. Right? So there's multiple reasons as to like what things could be called for problems. I know at least one problem in our code, so we'll start there. And again, debugging is always fun and painful. But one of the issues right now is this. Yeah.
On line 635, did you mean like parentheses EBP?
Yeah. That'll fix that one. I did mean EBP. That one definitely has happened before. So that one was my bad. And if we try again, we still get the wrong sum. So we fixed the segfault error. And the summation problem, though, has to do with this. So here, we're adding 1 to nums, right? What's nums type? What's nums type? Nums type is integer pointer. So if you add 1 to an integer pointer, how many elements should you move? 4, because it says move 1 int, right? If you add one to a short pointer, how much would you move? 2. And if you add one to a character pointer, 1, because the character is 1 byte big, right? If you add one to a double pointer, you should move 8. If you add one to a float pointer, you should move 4, because floats are 4 bytes big, right? It's the size of each of these variables is how much you need to move when you do the integer or the pointer and integer arithmetic. So you are again responsible for doing the translation, so you got to make sure that you do it right. Now the easy way to do it, instead of doing inkle, right, we might do something like leal, load effective address, the operation that we covered at the last time, right? And we want to move 1 times word size past EBX, and maybe we'll put that into ECX. And now ECX is equal to nums plus 1. We can push ECX, and there's no more need for the decal. What's the difference between this statement, leal 1 times word size, parentheses EBX, and move L? Yeah. Yeah, move L will move the value, and leal won't, right? Remember, they both do D plus O plus I times S, but then the move, or every other instruction, will then dereference it to get the values in memory at the location. Whereas leal will just compute D plus O plus I times S and then put it in the result. No dereferencing. So now if we do this and we recompile, I think we should get a correct sum. Right? So be really careful when you're doing the pointer arithmetic that you add the right amount. Leal is really helpful because you can do like complex additions to pointers very simply, right? But if you wanted to, you could use leal just to do arithmetic, right? If you want to do like EAX equals EBX plus ECX, you can use leal to do that, right? Because it's just going to do D plus O plus I times S. And if you just want to do EBX plus ECX, whatever happens to be, and put the result in EAX, fantastic. You can use leal there. No problem.
So did we get rid of like decal, well, instead of doing like this, decal E6, because like ECX is the new starter.
Well, ECX has nums plus 1, right, which we need to put onto the stack. But because we didn't actually increment EBX like we did last time, there's no need to decrement EBX, right? We didn't change the value in EBX, which is nums. So no need for that. Any other questions? Yeah.
So when you're pushing things on the stack before you call the recursive call, you have to push it like the same way that the arguments are called?
So when you call any function, be it recursive or not, right? If it's like following the GCC calling conventions, right? You have to always follow the same rules, which is arguments are pushed in reverse order of declaration. So if you have A, B, C, you're going to push C, then push B, then push A, and then do your function call, right? So again, our function is just C callable. Our recursive function is no different than any other function. You just call it after you push the arguments. Anything else? Okay, then let's show you some examples of like what this stuff kind of looks like. Don't pay attention to that. That's other classes stuff that I have to deal with. We're here. And then we're here. And then we're here in lecture, assembly. And then we might need a new Google Sheet, create and share. And this guy will be called stack view example. Okay, so let's say we have an example of some function. So let's say we have some function foo that takes in arguments a, b, and c. It has locals e, f, g, d, e, f, and it's going to wants to use, okay, maybe this is like a better way because, so here's our function, locals, extra regs, calls. Args. So over here, right, here's our function foo. It has arguments a, b, and c. It has locals d, e, and f. And it's also going to use ebx and esi. It's going to call function goo, right? And it's going to call goo with a b, e, f. Right? It's not really important what these functions do, it's just that they're being called this way. So over here we have function goo. Function goo has arguments, it looks like d, e, f, h, i, j, and k. And let me do this so that you guys can actually see things. Is that big enough? H, I, j, and k. It has locals L and M. And it's just going to be using ebx. And then it's going to call woo with H and M. And then down here we have function woo. It has arguments N and O. Let's say it has one local variable P, and it decides not to use any extra registers, and it's not going to call anybody. Do you want to go another layer deeper? Everybody want to go one layer deeper? Okay, we'll go one layer deeper if you guys feel like you need it, but for right now we're not going to. So let's see what does the stack look like as we're calling these functions. Right? So here's the stack. And then here's going to be EB, oops, probably want to put this up here. So here's the stack, here's EBP, and then here is ESP. So right before we call foo, what's the stack going to look like? What's going to be on it? Right, we're going to have C, B, and A, and then let's assume that main called it. We'd have the return address, right? So we'd have the return back to main, right? So over here, ESP is right here at this point in time, and EBP is somewhere up that we can't see it because we just got called, right? So we just called foo. What's the first thing that foo is going to do? Right? It's going to do the prologue, right? So it's going to push EBP, right? So over here, we're going to get mains EBP onto the stack, right? And then ESP is going to move down to here. Next step is to do what in the prologue? No, we push EBP, then move L, EBP, or ESP into EBP. So now EBP is right here, right? Next step after that is to make space for the locals. So we're going to have D, E, and F, right? And we'd also make space for the saved registers. Here we're going to have, I guess we'd have mains. It would be EBX and mains ESI. And now ESP has moved all the way down here, right? From all the subtracting and putting the things onto the stack. Any questions so far? Right? Again, notice that from right here, this is the start, or this would be like, foo's stack frame, right? Because we said that the stack frame is defined to be everything between EBP and ESP. So right now, this is going to be foo's stack frame at this location, all the way down here. Maybe we'll just paste that down here so that's clear. Or maybe we can just make this go a little bit this way. Sure. Yeah, I can drag it down. Or highlight it. I don't know. Sure. Anyway, it's there. Foo stack frame is there. So, any questions so far? So what are we about to do next? What happens next? Right? We're going to call goo. So if we want to call goo, what are we going to do? Push the arguments, right? So we're going to call goo with A, B, E, and F, right? So over here, right, the first thing that we would push would be like F, right, /K, right? It's the same thing depending on who's viewing it, right? Or, right, F right here, K right here, right? So we're pushing a copy of foo's F, which is going to be treated as goo's K, right? So that's why I'm doing F/K there. Does that make sense? And then the next thing that we would have would be E/J, and then B/I, and then H/A. And then ESP has moved all the way down here. Any questions so far? Right? I think this kind of goes to the question is like, what are locals and what are arguments, right? When we're pushing the arguments to call goo, right, we're pushing, foo's the one that's doing it, so he's pushing his local variables, right? But as soon as goo starts looking for these values after it's called, right, it's going to be treating them like it's arguments. Yeah.
Up in Foo's stack frame, why do we call vegan or add vegan instead of F?
So why is it FEBA?
No. Previously, so if you look at the map of where the stack is.
So why is it CBA instead of ABC?
No. Why is it DEF instead of F?
Oh, DEF instead of FED. Generally, space for the local variables is allocated in order. So you can assume that the variables would be pushed in order of the local variable declaration. So since locals would be declared DEF, you'd push D, then push E, then push F onto the stack. But it tends not to be terribly important as long as you're consistent, because the only function that's going to be dealing with the local variables is that function. So if it wants to do DEF or FED, it's fine as long as it treats them identically throughout the entire runtime of its lifetime. So we push our arguments, and then what do we do? And then we're about to call foo, or call goo, right? And so when we call goo, right, it's going to put what onto the stack? Right? This is the return to foo. Right? And again, ESP, which I think there's a nice, cool way of doing this. View, freeze, up to current row. And now, oops, undo. Oops. Just so that we can see this, view, freeze. Right, they should now stay at the top now. Right, and so ESP has moved all the way down to here. So we do our call, right? And what's the first thing that goo is going to do? Maybe I want to freeze a little bit more. What's the first? Because goo just got called now, right? We did the call. So what's goo going to do? It's going to do its prolog, right? Just like every other function is going to do. So the first step of the prolog is to save the stack frame, right? So here we're going to put foo's EBP onto the stack, right? And now we're going to take EBP and move it down to ESP. So ESP is right here, and we're going to move it, oops, from here, oops, to here. So now EBP has moved down. And then the next thing that we do after we push it is going to be make space for locals. We have two locals, so we're going to add L and M here. So L and M go onto the stack, and again, ESP moves down, and ESP moves down. And then we're going to need to make space for our locals, which are, wait, no, we did that. Then make space for EBX. So then EBX moves down here, which I should say foo's EBX is now here, according to what we said to do. And ESP has moved down to here, and EBP is there, right? And so this is basically where Goo's stack frame begins. It's going to start at this point in time because we finished our prologue. So Goo's stack frame is going to be from here and then on down. So we just okay. So we just finished doing Goo's prologue, and what's the next thing that's going to do? It's going to call Woo. So to call Woo, what's it have to do? Push the arguments. So which thing will it push? Right, it's going to push, M/O, right? M and O, and then H and N. And then it's going to call Woo, right? So then onto the stack frame, we're going to get to the return to Goo. And again, ESP has now moved all the way down to this point in time. Right, because we keep subtracting. So now we're over here in Woo. What are we going to do? Right, we're going to do the prologue, right? All over again, because that's the first thing that happens at the beginning of every single function. So yeah, we'll push EBP, right? So this will be Goo's EBP. Will show up onto the stack frame, right? And then ESP has moved down. Then we're going to move EBP to ESP. And so this is going to start Woo's stack frame right here. Right? Then we're going to make space for our locals. We just have one. So here goes P. And then ESP is going to move down. And then, right, we're going to run all of Woo's code. And then what happens at the end of Woo? The epilogue, right? But before we go and we start wrapping through the epilogue to see things undone, any questions about what the stack looks like? Yeah.
So where are all the operations between variables stored?
You mean like where's the actual instructions stored?
Yeah.
They're stored in the text section of your program.
So it jumps between the two.
Well, I mean, no. One is where the instructions are stored at, right? And that's where it's going to look to do read the instructions from, right? And then it'll be working with its data somewhere else, right? It's like imagine like you have a recipe, right? Your recipe is going to be on a piece of paper, probably held in your hands, and you're reading it, right? Or on your computer, right? Your recipe is not your ingredients. Does that make sense, right? And so you might go to your ingredients to mix your eggs and mix your flour and your chocolate chips or whatever else together, right? But you go over there to work with the ingredients, the data, right? And you look over here to follow the instructions. It's what you're supposed to be doing, right? They're two separate sections of memory.
But I mean, is the stacks like this all happens and then all of the ALU stuff happens, or like it's happening simultaneously?
So remember, like we're executing the instructions like push EBP, move L percent EBP, right? Add L, subtract L, right? Those type of things. So when we carry them out, right, those instructions are being executed by the ALU, right? Just where we're telling it to where the instructions are telling it to put some of the results of these operations is on the stack, somewhere else in memory. Does that make sense? Right, because you get a result from doing an instruction, right? And some of them are going to store the results on the stack.
So I guess what I meant is like as you're doing this, so between each of these steps, there's also arithmetic going on. Like,
Well, I mean, just as much arithmetic as your instruction says to do for like push EBP, right? That's the instruction you read in the text section, right? To carry out push, 5, what do you have to do? Subtract 4 from ESP and then move 5 to wherever ESP points to.
I guess I don't mean like the pushing pop, but I mean you want to all of a sudden add 5 to B.
So your question is, where is the instruction add 5 to B stored at?
Yeah, and when does it happen?
So it happens when you reach that line of the code, right? And that instruction is going to be stored in the text section, right? But the result of doing the addition is going to show up onto the stack, because that's where you said to place the result to. Any other questions? Yeah.
Does it matter if it's different files, like if you write the function different files?
Doesn't matter about different files, because when they all get linked together, they essentially become like one executable program, so they're one thing, even if there's dynamic linking involved. And that one program, it has one stack, not multiple stacks, and one text section, not multiple text sections. Yeah.
Kind of looks like the way we're doing it, we're adding it like downwards. Why don't we do it
Up top, because if you remember, we talked about the stack pointer, or the stack in Intel. The stack grows towards 0, right? So whenever we're adding space onto the stack, we get closer and closer and closer to 0. So like the top of the stack, right, is closer towards 0. So if we had like 1,000 and 500, 500 is closer to 0, so that's the top of the stack.
So the top of the stack in this would actually be like where P is.
Yes, right? That's where we have ESP is pointing to. Remember, the tip points to the top of the stack. And remember, our definition of the stack is wherever ESP points to, and all addresses higher than that, right? So ESP, the top of the stack, is always going to be at the lowest address. Any other questions? Okay, so we're going to start doing the prologue. What's the prologue say to do? What's the first step of the prologue? I mean, not the prologue, epilogue. First step of the epilogue. Right, we restore the saved registers if we have any, and then we move EBP, we move ESP, right? We move ESP to EBP, right? So where is ESP? Where is EBP at? It's right here. So ESP moves up. Then we do what? Pop EBP, right? So that says take whatever's on the top of the stack and place it into EBP, right? Well, what's on the top of the stack? Goose EBP, right? Which points to the beginning of Goose stack frame. Like you can imagine, like there's like kind of like an arrow from here back up to here. I just can't draw that in Excel, and if I don't do this in Excel and did it on the whiteboard, you guys wouldn't have a recording of it. So imagine there's a little line going back here, a pointer back to this line, because that's what's stored there, is a pointer. So right now what's going to happen is EBP is going to move from here back to here from the pop, because we put the old value, Goose EBP, into EBP, right? So EBP points back to Goose stack frame. And then we move ESP up 1, right, because of the popping. The next instruction would be to next instruction is return, right? And so return says take the value that's in the top of the stack and put it into EIP, right? Go continue execution from there. Well, what's on the top of the stack? Wait, it's goo, right? Go back to wherever we were called from in goo, right? So we're going to continue and pick up our execution from inside of goo. So we've reached the end of goo. What are we going to do? Goo's epilogue, right? And so what happens in the epilogue? We restore the registers, right? So we save some of them, which maybe I forgot to do. Did we put EBX? No, we saved. So we restore EBX back to being foo's EBX, and then move ESP to EBP, bam, all the way up here, right? And then pop EBP, right? So take the value here in EBP, or take the value on top of the stack, foo's EBP, and place it into EBP. So EBP flies all the way back up to here, because that's the value that we stored, right? This value links back up to here. And then this guy, ESP goes up by 1 because we did the pop. And now we return, right? So where are we going to return back to? Right, return to where we're called in foo, back to foo. So we go, we do whatever the else that foo does, and now foo finishes up. So what are we gonna do at the end of foo? Foo's epilogue, right? So foo's epilogue, what do? Well, we restore these registers, so we copy these values back into EBX and ESI, right? Then we move ESP or move EBP into ESP. So ESP flies all the way back up here, right? Then we pop EBP. So EBP gets removed, or the value in EBP goes back to wherever main EBP is at, wherever that happens to be at, somewhere else farther on the stack that we're not showing. And then ESP moves up by 1, and then we return back to main, right? Because we're on the where we're currently on the top of the stack is where main is at. We go back and we continue our execution for main. Does this make sense? I mean, it's still there, but is it considered part of the stack? No, because it's below ESP, not above it. So it's garbage now, right? This is why you may have had the issue where maybe you accidentally returned like a reference or a pointer to something that was declared on the stack, and it worked partially some of the time, but then later on you did some function calls and the value got messed up. It's because if you left the value on the stack, sure, you can have a pointer to it, and great, the value is there. But when you do more function calls, it's going to be overwritten, and then the value got like replaced with something else that you didn't want, and it doesn't work anymore. Any other questions?
You don't need a clear stack.
I mean, again, clearing the stack, when we cleared the stack, what did we do? We added to ESP, right? So it just changes where ESP points to, which changes what's considered to logically be part of the stack. But does that change the contents of memory? No. Right? It's gone. One thing that I also want to point out is notice that the stack frames are linked. So when I'm in here, right, Goo's EBP, this points back up to here. So unfortunately, there's no way to draw on top of this. Oh, I have an idea. Well, no, that's a bad idea. I can't show everything. Right? So this guy right here, he points back to here. This one points to, nope, points, Foo's EBP points back up to here, which then points back up to main. So you guys may have used in like GDB or DDD, there's a command called backtrace, which shows you the functions that were called and allows you to go back up the stack to see what the values of the variables were in the calling function. This is accomplished because the stack frame pointers are linked, right? For my current function, I can actually go back and access my previous function's local variables as well as arguments. And from that function, I can go to the function that called me and access its local variables and arguments, and then go back up and access its local variables and arguments. So again, notice that a function, it has access to all of the functions that called it, their local variables and arguments. Now we'll pick up with this on probably Thursday because I don't think I have enough time to show you the example. But think about how you would write code given, let's say, we're currently inside Woo. How could we access the C in Foo given we're currently running Woo? Does that make sense? Given that you're in Woo, how could you access Foo's C, right? Foo's argument. Or how could you access Foo's E? Something that was never passed, or, Foo's D. Something that was never ever passed to any of your functions. Right? You can totally do it if you exploit the fact that the pointers are chained and you're able to go back up. I'll see you guys either in office hours or I will see you in class on Thursday. And then Thursday we'll do that example and then we will do inline assembly, which is what you need to finish your final project.
Professor?
Hmm?
I really don't know how I'm going to finish these 3 problems in time. Like, I've started on half stack.
Yeah, I said we're going to give you more time.
Wait, you're going to give us more? Wait, you're going to extend the deadline?
Yeah.
Oh, I didn't hear that.
Yeah, I thought we had less time than we did, so I'm going to give you probably
Oh my
another
God,
half a week to a full
My
week.
head, I was like, oh. He's like, I have a midterm tomorrow. I'm like, oh my God.
Yeah.
Oh, thank you so much. Oh my God.
I didn't realize how much time we had left when I set the due dates. I'm like, so it's a little bit too early.
I was so scared.
I thought we had a week less than we did.
Okay, good. Well, we're still coming to office hours today.
Yeah. See you in a couple minutes then.
Oh, by the way, for the the knapsack with that first problem that took you 3 hours, but you said it'd probably take us less time.